Example for class 16, and here's my big head. Make it a little bigger. All right, so I created this example. Just wanted to demonstrate using stress concentrations for multiple stress states. So we got this little part, and we're loaded up the end of it, and it's got a material of 36 KSI. Boom, boom, and it's 6 inches long. It's 2.75 inches in diameter here, but it transits to a larger piece that's 3 inch in diameter, and it's got a fillet of 1/4 inch, and it's got this loading of 2,000 downwards, 1,750 over to this way. It's got an axial of 20,000, which is much larger than the other two, and then it's got a 15,000 inch-pound torque. And we're going to highlight that this is what we're going to use for the nominal stress. So here's what the area, moment of inertia, and polar moment of inertia are going to be. So by inspection, we can get the loads. We could do a free body diagram on this, but we're pretty easy to say that about the z-axis, we're taking that 2,000 and multiplying it by 6. And similarly, about the y-axis, we're taking our 1,700 and multiplying it by the 6. So we get this. These two, but we're going to look for the worst location because we care about where it breaks mostly. So we want to find, we're going to take those two moments and we're going to find the maximum moment that's going to be on it, right? So it's being bent down and it's being bent towards us, right? And do I have, right? So it's being bent down and it's being bent towards us. So it's being bent diagonally, right? So you can expect up there is where the tension is going to be the most. Now we get the stresses. Axial is obviously in tension. And look at my hair, nice hair there. Bending is going to be both tension and compression, but they're going to combine with the axial, so we might as well use the tension side of the bending. And then torsional shear is going to be this value, just TR over J. So we go and we want to find the stress concentration factors for this scenario, and that's in figures A15, 7, 8, and 9. And we're going to use the ratio of the big diameter divided by the little diameter and the radius divided by the smaller diameter. So here is the 3 figures, and right there is about the location of it, right? So we got 0.909 right there. You can see it here in all of these. And we have 1.09, like we have 1.1 there. We actually have 1.09 here, and we have a 1.1. So based on my very careful analysis of this, I was able to find these stress concentrations to the best of my ability. And if you don't believe me, I actually have done, let's see, yeah, I've actually done these, right? So what I've done here, let's see, I could show you, let's see what I gotta look at what the values are. So I have 0.909, right? I could go back to my 0.909 and 0.0909 right there, boom. And I can make this smaller right here. So what did I say that the factor was here? I gotta look back, I gotta look at the time too. I said it was 1.58. So I could double check with my 1.58 and boom, you can see where that goes. It's just below that 1.1 because what I've done is I've superimposed an Excel graph and I picked a bunch of data off of these things. Yes, I know, I have no life. But anyway, so these are the stress concentrations for each of these. And even though this is a ductile material, we're going to use the stress concentration because we want to compare this to FEA. So there you go. Here is for the axial. It's a multiplier. So here's what the value that we get in KSI. Here's the torsion. And then here is the bending. And we're going to combine the axial and the bending together. And so here is the overall stress state at some element. It's kind of like, it's not necessarily aligned with any, it's not aligned with any of the axes except for the x-axis. So you see that I didn't bother putting in what that axis was, because it's something diagonal. But now we can find the absolute maximum shear stress. And because it's uniaxial, I can use this equation, and I get 9.871. And then for von Mises, we could use this uniaxial as well. We get 19.26. And for our safety factors, dividing it by 36 by 2 to get the shear yield, and dividing it by the absolute maximum shear, we get 1.82. Doing the same thing, not the same thing, but doing the safety factor for the distortion energy theory, we take the yield strength, divide it by the von Mises, and we get 1.87. And just as we would normally think, we are just a little off, right? They're just a little different from each other. And the maximum shear stress theory is less. Right, and so if we were to go onto this shear envelope, actually I only do this as maximum shear stress theory. That's interesting. I need to go back and fix this thing. But here's that data point. You could see where that data point is. It's not. This is really close to where these guys would intersect right there. So I need to actually redraw this onto here with the von Mises on. But I did make an FEA of this thing. And here are my results with a pretty tight mesh. Look at that. That's about as good of a mesh in SOLIDWORKS simulation as I can get. And I'm predicting, according to this, maximum of 18.61. I think actually I got a different one where I got like 18.7. But you could see compared to what we're predicting here, 19.26. Not great, decent, but it is an interesting outcome, right? But that was some of my point in applying the stress concentration factors to in the three different loading modes that we had. We neglected transverse shear in this case, but we could mess around with the mesh some more, trying to get this more and more refined. I already have the slider all the way down. I can try to make that a smaller, but a lot of times that will just it can only go so far before it decides to crash. Sometimes you can mess around with it with different kinds of combinations right here. Oh, it meshed. Okay. Oh, that was quite dense. Let's see what happens here. Let's see if it gets any higher. I don't know. Maybe it won't. I don't know what the answer is going to be. Hitting it and solving. It doesn't make a lot of sense to really ramp this up all the time. Makes you have to wait. I don't like waiting. I guess other people do like to wait. Is that true? Oh, it actually went down. That wasn't expected. It's a pretty tight mesh right going on right there. But anyway, it's a comparable thing, right? And doing this mesh sensitivity study onto this to see, I almost wonder if I made that a little bit tighter. So what if I were to edit this definition here and then also not only click on that surface, but to click on that entity right there? I probably will mess the whole thing up. What do you think? Maybe? I don't think that improved it any. I don't think so. Let's run it. See, I gotta go to class here in a minute. I gotta get my papers ready for going to class. We're gonna use this book and run you. Didn't grade those. Any better? Let's see. Nope, same result. Okay, well, video's over then. Be that way. We'll do another example maybe after this next class. Maybe. I don't know. We'll see.